I'm pleased to invite Shmuel Bialy, who came from here not so many years ago. Spent then 3 years in Harvard, and now he's in Washington, and he will tell us about what? Maryland. DC, from my point of view.
The other Washington is on the other side.
Too far from Harvard to the other Washington. So, and he will tell us about how dust affects formation of stars. Please.
Thank you, Lev. Switch off the lights. Lights.
Yeah, good now? Okay. Thank you, Lev. Thank you for inviting me here to talk about how stars shape interstellar gas and dust. As Lev mentioned, I came from here. I know many of you, and it's nice to be now on this side of the room. So in this talk today, I want to talk about this idea of feedback, how stars in different forms through supernova, cosmic rays, and UV radiation affect and interact with interstellar gas, out of which they form. They form out of this gas, and as we'll see, they then affect this gas and interact with it in many different interesting ways. This is work that I've been doing with several people, several projects in Harvard, Alyssa Goodman and collaborators, Vienna University, MPA in Munich and Florence. So just before we dive right in, let's just step one step back and just look at the big picture. Well, that's not an astronomical observation, although they sometimes look kind of similar. But like when we go outside and look at the sky, we usually the first thing that comes to our eyes is the stars, right? And that's the Starry Night by Van Gogh. So, however, in fact, there is much interesting stuff going on between the stars. And that's what generally called the interstellar medium. That's all the gas and dust between the stars. That's an all-sky view of, let me try to move this away. That is possible. Yes, thank you. Thank you, Lev. So this is an all-sky map of the galaxy, the Milky Way, taken with the recent satellite Gaia. What you see is the light from the star that is illuminating in the center. That's the Milky Way galaxy. But you can also see lots of these cloudy structures. These are dusty clouds, some of which molecular, some atomic, that fill out the void, the space in the galaxy, in the Milky Way, as well as in other galaxies. And these are very interesting and important. That's where these stars are forming. That's where all the action is happening, in these molecular dusty clouds. And that would be the topic of this talk. So let's zoom a little bit more onto one of these clouds. And what we see here is the basic cycle of interstellar gas that is happening in our galaxy as well as in other galaxies. If you look at the baryon, at the basic particle in the galaxy, it goes through this cycle. So let's say you start from the interstellar medium, which we just discussed, which on large scales is mostly atomic. So you're in atomic form somewhere in the galaxy, in between the stars. And what is happening is usually you have a cooling going on, a radiative cooling, where you have collisional excitation followed by radiative emission of photon lines and the continuum that escape from the galaxy, and therefore you have cooling. Generally speaking, the interstellar medium and the galaxy is very non-adiabatic system, right? You have always heating from stars and supernovae and other sources of energy within the galaxy, as well as cooling through these collisional excitation followed by radiative decay, which cools the gas and take out energy. So that's just like on large perspective. So the atomic interstellar medium cools off and becomes denser and colder and forms molecular clouds. this is where stars are forming. These clouds can then further collapse via the action of gravitational contraction. They continue to collapse, become denser and denser until finally it reaches high enough densities and pressures, and that's the point where hydrogen fusion kicks in, and then you have a star. Once you have stars, these stars now feed back on the interstellar medium. They emit radiation, they emit winds, which shape back the gas around them. And finally, they explode as some of them, if they're massive enough, they explode as supernova, injecting even more energy into the interstellar medium. These two processes generally, as we'll see, try to inhibit further star formation because you inject more energy. In some cases, they can promote star formation. That's the topic of this talk, or partial topic. Then this gas cycles back into the interstellar medium, and so the cycle begins again. This is also, by the way, how, and you heard recently from Hagai about this, how many of the elements are formed in these supernova remnants or supernova themselves or the stars. So that's also the way to produce new elements. But the general idea of stellar feedback is what I want to concentrate today. That's very important. So stellar feedback, when I say this, I mean all these forms of energy, UV radiation, winds, supernova. And we'll also talk about cosmic rays, so high energy particles that are also thought to be accelerated in these supernova remnants, and they also interact with the interstellar medium. And generally speaking, they all interact with the interstellar medium in different ways, shaping it. By shaping, I mean they determine what would be the temperature by heating processes, the density, the chemical state, the formation of different molecules, and the coupling with magnetic fields, because they also produce ionization and therefore coupling to the magnetic field of the galaxy. And by this, they also regulate or self-regulate, if you wish, the star formation rate in the galaxy. In this talk, I'll focus on smaller scales of the galaxy and even clouds within the galaxy. But just before I do that, I'll mention that this idea of stellar feedback is important even on larger scale of the universe as a whole. So for example, here we see the famous cartoon of the evolution of the universe, starting from the Big Bang, where it was hot and ionized. Then we had recombination. From this point onwards, the universe was mainly neutral. And this is called the Dark Ages, where you don't have stars yet because gravitational collapse was not effective yet. At some point, you have the formation of stars, galaxies, first galaxies. At this point, the universe was again reionized. Today, we think this happened through the action of ionization by stars and galaxies from these first galaxies. So the ionizing radiation or the stellar feedback on large scales also was the mechanism that reionizes the universe as a whole. But as I promised, today we'll focus on smaller scales of clouds. And in particular, I'll separate my talk into 3 parts. I'll really talk about these 2 and maybe mention in one word the last one. The first one is how do supernova affect the interstellar medium? And the second is how do cosmic rays affect the interstellar medium? Cosmic rays are accelerated by supernova, so it's not disjoint. But as we'll see, it also affects different parts of the cycle that we saw before. So let me start with the supernova. By the way, I forgot to put on my watch, so you can tell me like, I don't know, sometime. There is? Oh, okay, great. Yeah, I love this old tech. It's very useful. Okay, so let's start with supernova. So the idea of supernova interaction with the interstellar medium has been studied already from the 70s, and that was a seminal paper by Chris McKee and Jerry Ostreicher, predicting that if you consider the rate of supernova in our galaxy, or star formation rate in our galaxy, and the effect of heating and ionization by the supernova remnants, you basically get an interstellar medium that is full with voids, with hot gas that occupy a large and significant fraction of the volume. And in the rest of the volume, you have neutral gas that can be colder. These are 2 cartoons from that paper. So for example, what we see here are a cartoon version of what is happening. You have supernova remnants that expand outwards from the powerful explosion of one or even several supernova, clustered supernova. And then here inside, you have hot gas that sweeps up clouds of colder, denser material and basically destroys these clouds that may be molecular and otherwise start forming, but this hot interior, the thermal conduction hits these clouds, and therefore they start forming. So that's, for example, this is an example of negative feedback where the supernova inhibits further star formation through this thermal conduction and destruction of cold, dense clouds. A more modern view of this same process, or generally the three-phase interstellar medium, what we'll just have a look at, this amazing suite of simulations called the Silk by Walsh and collaborators. This is MHD simulations where they have cooling and heating, all these cooling and heating processes I mentioned, as well as on-the-fly chemistry, formation of molecular hydrogen, CO, and some other molecules. All these feedback processes, namely supernova, and of course gravity. And what we're looking at is if you imagine like you have a galactic disk and you just look at a section, and that's a section in the XZ direction, so you have up and down. And here this is a face on where you look down at the galaxy. And we're looking at different fields. So here we look at density, temperature, density projection, and different phases, H+, H, and H2. I'll just run this movie just to get an impression of what is going on in a simulated galaxy like this. So first it's a phase of initial conditions, and then you see that the dense clouds start forming stars. They go supernova after a while, or after a few tens of mega years, and then you have this hot phase of a few 10 to the 6 or even 10 to the 7 Kelvin hot ionized gas, and then you have the cold materials that is sometimes totally destroyed and shredded, and sometimes it's pushed away. And there's lots of studies going on, and I just showed this for impression of how this looks like and just a general feeling of the multi-phase interstellar medium that you get at different temperatures and density that are encountered. Yes?
What are the small circles in the density map?
These are star clusters that are forming when the density is high enough and the temperature is low. Then they turn on a star particle, and these are the particles that then inject back the feedback into the simulations of supernova and winds and so on. Okay, but on the other hand, supernova can also have a positive aspect of the feedback, and that's quite surprising if you think about it. But here how it works. So as I mentioned, the interstellar medium is non-adiabatic. You always have active cooling and heating processes. And heating is mainly from the UV radiation coming from the stars, specifically far UV non-ionizing radiation. And cooling is by collisional excitation, which excites levels, molecular levels or atomic levels, and then you emit a photon, and the density is very low, so usually the photons just escape the galaxy. Now, here is what happens if you consider the cooling and heating processes, and you ask yourself, at a given density or the given temperature or pressure, what is the solution if I ask what heating rate equals cooling rate? So this is the phase diagram, if you like, of the interstellar medium. So now we are talking about the neutral medium, the neutral atomic gas. Here we look at the number density in particles per cubic centimeter. So very low densities. I'll make the analogy in a second. This is the thermal pressure, and every point on this curve obeys every point on this curve obeys the equation of heating equals cooling. So you're in a thermal steady state, not cooling, not heating. If you're above this curve, so for example, at a given density, if your temperature is higher, you're above this curve, and then typically the cooling curve is such that cooling is very efficient, and then what is happening, cooling is greater than heating, and if you're isobaric, then you cool down to lower temperatures and higher density. If you're below this curve, heating is greater than cooling, and then you heat up. Usually the way we look at this is we think the pressure is set by, for example, the hydrostatic pressure, like the atmosphere on Earth. So you're squeezing the atmosphere of the galaxy by just its own weight. So the pressure is set, and then you ask yourself, what's the temperature and the density given the heating and cooling processes there is? Actually, there's a very beautiful analogy with water vapor and water liquid and the phase transition between the two that is made by Zeldovich and Pickelner, where you have, if you are at very low densities or low thermal pressures, you're in the warm neutral medium, that's the gas phase of water. And then as you increase, you have the mixture between the gas and the water. And then if you further increase the pressure, then everything becomes cold. And that's analogous to the liquid water. And this is analogous to the phase transition. I'm saying analogous because it's not a real phase transition. We're still talking about gas. Right. That's why I'm saying it's
not equilibrium.
Right. That's what I'm saying. That's why I'm saying.
Losing all the time the notions of.
Yes, because I think it's beautiful to make the analogy, but it's different. It's not real phases. It's all gas, and it's not adiabatic, so it's just analogy.
Also, there is no difference between the phases in liquid and gases. Okay? So they are have the same symmetry. So there is no difference. But the question is do you have here any difference? Do you, for example, have here supercooling or superheating?
No. It's not phases. It's okay. I agree. It's not phases. I say phase in phase, not real. Okay. We call it phases, but it's not real phases of classic phases. By the way,
what happens in the middle of this?
So if
in the middle of the
right, this is here you have a thermal instability, and you can have both two phases coexist. If you're at this thermal pressure, you can have the most of the volume is filled by the warm neutral medium, and then you have pockets of cold neutral medium in between that are in pressure equilibrium between the two, the same pressure, and also in thermal steady state where heating balances cooling. You have a multi-phase, and this is, by the way, what we think the galaxy is, the situation of our galaxy, that we are at this thermal pressure and we have a multi-phase. That's part of the explanation for the clouds. The pressure that we talk about is very low compared to Earth. Yeah, just to compare this thermal pressure of this is units of in K Boltzmann, the units here, and CGS divided by K Boltzmann. This is 3,000, and if you convert it to MKS, that's 4 × 10⁻14 Pascal. That's 4 × 10⁻19 atmosphere, and in CERN, it's from what I read, it's about 10 to the minus. They go down to 10 to the minus 13 atmosphere. So this is a serious vacuum, even when we talk about like clouds and everything. But it's not a problem. It just means that everything takes longer, and there are some processes that are different. For example, as I said, that excitation usually emits photons that just escape the system rather than being thermalized. Now, if we look at the phase diagram, starts from here. Okay, at higher densities, lower temperatures, that's where gravity can kick in and further collapse the clouds and help to star formation. So if we start, for example, from what we said, the galactic conditions where you're at a thermal pressure of about 3,000, and most of the volume is filled with this warm neutral medium, the question is, how do you go from here, from a state that is not star forming, to higher densities, colder pressures to here? How do you jump above this thermal instability? And that's where supernova can help. It's not the only way, but it's a very attractive way. And the idea that as the supernova remnants, they expand at first, yeah, the interior is very hot and destroys molecular gas and cold gas. As you wait longer and longer, the velocity drops, becomes smaller and smaller. It's still supersonic, but it becomes mildly supersonic, maybe Mach numbers of a few, 2 to 5. And at this point, you still have a shock. And what happens is you have a shock, so you jump up, to higher densities and higher temperatures and higher pressures. And then at this point of the curve, you already have a cooling that exceeds heating, and then you start to cool down towards the cold medium. So basically, this is the route you follow. On the cooling time, it takes about 1 to 10 mega years. That's what simulations show. So this is supported by analytic models and also by the simulations I'll show you in a moment. But basically, the simulations that we saw before Silk find this, as well as analytic models that you just drive a shock and follow the radiative compression. Yes.
Sorry, but so you said this is not the only way, because like I imagine that the first star is formed, you should have another mechanism.
For sure. Also even in our galaxy. So
is it just normal cooling with molecules like H2 or this kind of stuff? Or do like
well, it's always normal cooling. Also here it's normal cooling. Yeah. The thing is you need some perturbation, something to jump above this thermal instability. And for example, another way that you can do that is by falling into spiral arms. So if you have some asymmetry in the gravitational potential on large scales of the galaxy, i.e. spiral arms or a bar or something like this, or inflows from outside galaxy, then you can have. But you have to have something supersonic, mildly supersonic, to give you this shock. Once you have the shock, then you jump above this thermal instability, cooling exceeds heating, you start to cool. Still, it's not easy. You need the shock to be there for long enough time because you want it to be there for at least the cooling time, this 1 to 10 mega years. Otherwise, you shock heat and then you come back. So you need to continue compressing until you get above this thermal instability. So just to show how it looks like, again, the Silk simulation, edge on view, face on view, we have here supernova exploding. These are particles that follow, tracer particles that follow the distribution of gas. And what you see here is the void is formed because of the supernova that pushes all the gas out. But then at the edges, the gas accumulates and then also goes through this thermal instability and thus becomes very dense and therefore forms clouds of molecular and dense gas that then will form again stars and so on. So this is a form of positive feedback. So just a few words on observations. This really, the work moves from observations where people were looking at regions in the galaxy where there's star formation and try to see if there's some positive feedback effect like this. But really to see this in action is really problematic because we're talking about, as we said, 1 to 10 mega years. At this point, the supernova remnant is already expanding and is not very spherical. It's not glowing in X-rays. Observationally, it's very problematic and difficult to see this. This until now. So we think maybe for the first time, we see something that resembles this positive feedback formation of molecular clouds in 3 dimensions. And how was it possible? Because traditionally, all observations in astrophysics is 2-dimensional, right? You look at the sky and you just see the plane of the sky. You don't have the notion of the distance. And that's very problematic, like here, right? We have this person here and these ones. They're standing in the Salar Desert in Bolivia, where the floor, it's very difficult to say from the floor where this guy and where they are standing. So you don't know where the distance. When you don't know where the distance, it's very difficult to say if you're just seeing something that is close or something that, if something is very large because it's large or just because it's close. And that's why you get these funny pictures, or there are many of them, but we'll look at them after the talk. And that's what's happening in the interstellar medium. You see these clouds like here. And for example, these are 2 famous molecular clouds in our solar neighborhood about 500 light years away, the Perseus and Taurus molecular clouds. And you don't know, for example, if they're really touching or if it just so happened to be along line of sight, and what are their sizes, and just generally, what's the distribution of gas? You can't really see a shell because you don't have 3D. You have a projection, but the ISM is not perfect. It's not like you have perfect shells and you can see this projection very well. So recently, it became possible to get observations of the interstellar medium in 3D. The basic idea is that when you look at stars and you look at their light, it is extincted, it is absorbed by dust along the line of sun. So from the amount of light that is absorbed from the stars, you know how much column density, not density, but column density, how much mass of dust there is between you and the star. I have several stars, you know how much delta in column density. Yeah, this one. How much delta do you have between this star to the next? How much material there is. Now, recently, we also had very accurate distance measurements by this satellite, Gaia, which gave us very accurate distances to these stars, to these beacons of light. So now we have the amount of dust and we have the distance, the delta distance between the two. So we can know what is the density of the gas. So people here at the MPA, they worked very hard, collected all the light from all the data from Gaia and all these extinction column densities from the stars to build, for the first time, a very high resolution, three-dimensional map of the density of our interstellar environment. And this is what we saw. So these are, again, the two molecular clouds that we saw before. This is the Taurus and Perseus molecular clouds. But now we can lay in 3D. So first of all, we see that they are not actually touching. They're at very different distances. This is something that actually has been known before. But something new that now we can look also at lower density gas, shown now in white. And as you can see, we now see that these two clouds are embedded in lower density material. This is about 5 particles per cc per cubic centimeter. We now find that this material is actually arranged in the geometry of a non-ideal spherical shell. So what, and this is more statistical analysis of this of these dust mats. So these are different density cuts through the region where you have this semi-spherical shell, and Perseus and Taurus is embedded within it. This is radial cuts of different densities as you go from the center of the shell where there's almost no gas or dust outwards. You can see the peak. The peak is at about 80 parsecs, which is 8 by 3, 240 light years. That's the radius of this shell. So what we think is that here we have the first case, and again, possible thanks to the three-dimensional observations of molecular clouds that are embedded within the shell. From energy considerations to form this shell and the velocity that we observe, we think that we calculated that you need at least about 2 to 8 supernova, so it's more than one in this picture, have a series of supernova. In fact, this is expected because we know that most massive stars are formed not separately, but in clusters of many thousands of solar masses or more. We estimate here that you'd have about thousands of solar masses for the stellar cluster. And the age of the shell, based again on the radius and the velocity, we estimate about 10 mega years. So in agreement with what you'd expect from this theory of cooling. We have some evidence for the progenitor, for the supernova, although it's not clear. We'll still need to look into the stellar data and trace back the stars from Gaia and see if they all align into a cluster in the past. But this is an observation from E Rosita in X-rays. And the green circle is the projection of the three-dimensional shell on the two-dimensional sky in X-rays. And here the red circles just show the region of enhanced X-ray activity, which suggests hot gas produced by ancient supernova. But the real smoking gun would be if we observe a cluster of stars that belongs to this at the right age, and this is something we're working on now. So just to summarize this part, and then I'll briefly talk about the second part. So to summarize this part, there are two stories. One, going from 2 dimensions to 3 dimensions really reveals new structures. This is one example, but really the map, the 3D dust map is much larger. I'll show you in a second. And there are much more to be explored and to find out if most of the volume is like this, composed of these supernova voids, or is it a coincidence, or what are their statistics, and so on.
Again, what is the time scale between the explosion of the supernova and the
About
forming?
10 million years. It takes time. You need to wait. More than a PhD. And then we saw that supernova can inhibit star formation and formation of clouds, but it can also promote star formation through shock compression and condensation of gas. Yes.
This scenario of supernovae star formation. Say a few words about the role of the central black hole.
Yes. So in this scenario, the central black hole does not, a central black hole does not play a role. I mean, we're talking here about masses. You mean central black hole like in the galaxy, like a supermassive black hole, or just like the
A supermassive black hole central.
Center of the galaxy.
yeah. So this would be a different mechanism on different scales. So in AGN, active galactic nuclei, where you have this supermassive black hole, like in our galaxy or in others, these if you have activity and gas around it, you have very explosive feedback, very energetic, that drives also shells and very strong winds on larger scales, on galactic scales, and even beyond. What we talk here is more like normal environment. So if you look at an environment like our solar system, or like the solar environment, where this
Far enough
from the center, yes. So then, yeah, so we concentrate on these more, less active and explosive environments than what is happening in AGN. Here is just a look at the full map. I did some radiative transfer in MATLAB to view this. This is the full map that spans 2.4 on 2.4 and 1.8 thousand light years cube. It's a lot. So the region we just looked at would be like a small sub-region within it. And this is really a new map, a new observational database that we have, that we just start exploring now. So I'd like to, for example, look at the statistics of these shells, supernova shells, how this agrees with the supernova rate and star formation rate we have in the galaxy. If you connect this to spectroscopic observations of CO and H1, where you have Doppler shifts that tells you the velocity, then you can have 4D. This is a quest by its own. It's not easy because you don't have these observations in the dust. So you have two separate data sets that you somehow have to need. But if you do, then you get 4D. You have the 3D plus velocity along line of sight. Then you can constrain the kinematics much better. And finally, the connection with the stars themselves, which then go supernova, where you have also now 6D information from Gaia. We have the 3D plus the velocities on the sky and radial velocity. Yeah.
More technical question. So this is all based only on the dust extinction.
Yes.
To these Gaia stars.
The structure, yes. Then, yeah. In the paper, we also go on to additional evidence of, like X-rays, aluminum 26H alpha. And
How based just on the Gaia photometry do you derive?
okay,
How do you know how much extinction, how much dust?
Yes. So basically, this it was done by this group of Blake et al. And basically, what they do, so you have the spectrum from all, not spectrum, but in different bands coming from the stars, and then from the shape of the extinction, you kind of guess or you model what's the star type, and then you know what should be its luminosity. So you know it's.
We'll talk about
Yeah, we can go into the details. But basically, it's a technique that has been there for a while. The news is that now with Gaia, the parallax measurements became much more accurate. But generally, the idea of 3D dust map has been there for like 10 years. But now with Gaia, we go down to a resolution of 1 parsec, where before it was like, I don't know, tens. So you couldn't get all this structure. So this is the dust map. Okay, so this is about the supernova. In the rest, maybe 5-10 minutes, 10 minutes. I want to say a few words on the cosmic rays. This is totally different story. More about atomic physics, as you'll see. The cosmic rays we think are produced mainly by supernova, so it's connected. From the point of view of interstellar medium, the connection is much more natural. If we go back to the cycle we saw before, we had the cycle, remember, atomic ISM going to molecular gas, star formation, stars, supernova, and so on. Now let's focus on molecular clouds, regions that we talked about of higher density, dusty material. This dusty material, the dust, absorbs the UV radiation. So the UV radiation doesn't play a role in the depths of the clouds. It's absorbed in the envelope. What's happening inside the molecular cloud? What hits this molecular cloud? What dominates the chemistry, the coupling to magnetic fields? It's all cosmic rays, so high energy particles, non-thermal particles that are, we think, produced by supernova, as well as, in fact, other sources. These cosmic rays can penetrate, they have lowered cross sections, they can penetrate into molecular clouds, and these cosmic rays doing everything. We're talking here about low energy cosmic rays, that's a below GeV or TeV or so. These cosmic rays are more abundant and they have a higher cross section. So what they do, they produce ionization. They ionize the gas. The secondary electrons, typically of energy 30, 40 electron volts or so, produce many secondary electrons of these energies of 30 electron volts. These secondary electrons, they drive the chemistry. They heat the gas, determine its temperature. They couple the clouds to the large-scale magnetic fields of the galaxy. I say they drive the chemistry because we are talking about very low temperatures, 10 Kelvin or so. At these low temperatures, you barely go beyond any chemical barriers, but these secondary electrons and the ions produced, they drive the temperature. Yet, we have quite little knowledge about their spectrum, the shape, the abundance of these cosmic rays. So here, for example, is a plot of the spectrum or the flux of cosmic rays as a function of the energy of the cosmic ray nucleon. This is observations from the space station, and these are observations from Voyager, which actually left quite recently the solar system. But still, we think that the Voyager is still influenced by the local environment. For example, there might be a possibility of a bow shock as the solar system sweeps into the interstellar medium of the galaxy, as well as on larger scales. We know that the solar system is embedded in one of these voids that we just talked about, that are called the local bubble. So basically what I'm trying to say is that the Voyager, while very useful, it's not providing us the spectrum of the real interstellar spectrum of cosmic rays. It gives us the local spectrum of cosmic rays, but not the typical spectrum we expect in the interstellar medium of our galaxy. The question is, what is it? So for example, here are 3 models for the slope, and we don't really know which one is it. So this one, or...
Is that protons or what?
Protons, yes, protons.
It could be neutrinos that we have no idea about.
Right, but for our purposes, if we think about if we are talking about the molecular clouds and the interaction that I discussed, like the ionization and then the production of electrons, chemistry, heating, that would be about GeV protons that dominate these processes. So how still do we know about these cosmic rays? The main way we infer these the abundance and the ionization rate of these cosmic rays. Here in this plot, this is showing the rate of ionization of a molecule in a molecular cloud in the galaxy as a function of the Coulomb density. That's a measure of how massive is the cloud. And each point here is in the measurement that is made this way. So people observe using spectroscopy to observe different molecules. For example, H3 plus here, HCN, different molecules in these molecular clouds, then what people do, they use chemical models that say, given the observation, given the amount of molecules we see, the cosmic ray ionization rate should be this and that. Otherwise, it doesn't agree with our observations. The problem is that these chemical models have uncertainties, and there are many assumptions that go into these chemical models. Plus, these molecules are not the main constituent of the gas. Most of the cloud is H2 molecular hydrogen, but H2 you cannot see. So what people see, look at these bizarre or more esoteric molecules like H3 plus, HCN, HCO plus, argonium H plus, and you name it. So that's the problem, and that's why there is quite a lot of uncertainty about the cosmic rays and the cosmic ray ionization rate. Now, recently I had an idea. How can we maybe have a different way to measure these cosmic rays in molecular clouds? And that's to use the H2, the main constituent of the gas, directly. How does it work? And Lev here knows the background story because he went eating with me lunch. But I'll tell you later how I came to this idea, but never mind. How does it work in terms of physics? So you have H2 molecule. You have a cosmic ray. In fact, it's the secondary electron produced by the cosmic ray that collides with the molecule. Typical energy is about 30 eV or so. And then here we have the energy diagram of molecular hydrogen. So this is the distance between the two nuclei. This is the energy. And here we have different rotational level with different J of the molecule, different vibrational levels, and this is the electronic levels of H2. Basically, the electrons, they excite these levels, and specifically, they're very effective at exciting the first vibrational level, the first rotational levels of H2. Now, what happens when we're talking about the interstellar medium density is low. So once you excite, you usually de-excite, not collisionally, but radiatively. Yeah, the Einstein coefficient is higher than the collisional de-excitation rate. And therefore, you emit a photon, and the flux in the line is directly proportional to the collisional excitation rate. So basically, if you observe this infrared photon in the infrared, you get information on the excitation rate and the ionization rate as well of these cosmic rays. In fact, similar techniques were used in the past, not in the context of cosmic rays, but molecular hydrogen excitation by UV radiation in regions of active star formation. So here is an example spectrum of molecular hydrogen where it's excited by UV, or collisional excitation in regions where shocks are effective, where the temperature is high. But never it has been observed with excitation with cosmic rays in dark. That would be dark, cold molecular clouds. That would be your ideal probe, right? Because you don't want all these other excitation. And yeah, so basically, if the cosmic ray ionization rate is high enough, the prediction is there are four lines. These 4 lines of V equals 1 to 0, first vibrational level, and first J equals 2 and J equals 0 to 0 and 2. These 4 lines are preferentially excited by cosmic rays, and the ratio of these lines to other lines would be higher for cosmic ray excitation. And the prediction is you might be able to see this in typical molecular clouds like in our galaxy. And we went ahead and tried to do that recently with the MMT as a telescope, infrared telescope in Arizona. We went and looked, we got time to look at the 4 molecular clouds, 6 nights. This is the spectrum. The line is expected to be seen at 2 microns. And here you go. No, that's not the line, that's the sky. That's the sky. The sky in these wavelengths is very naughty. It's very bad. So we were not able to detect the line. We were able to place limits on the cosmic ray ionization rate in the clouds and the slope of this power law spectrum based on the non-detection. Basically saying what we see is what we see. If the fluxes were higher or the slope was steeper, we would have seen a line, which we don't. So basically place a limit on the spectral slope. We exclude some regions in this parameter space. But the real news is, I'll skip this. The real news is this, right? Some of you may know, next month is going to be a big month. This thing, the JWST, James Webb Space Telescope, is going to be launched in space. Hopefully nothing happens. James Webb is going to observe the universe in infrared, and this is one of the wavelengths. And predictions for the spectrum with the with the calculator and the tool predict that we should be able to see these cosmic ray excited lines with high signal to noise. This means if this is approved, that we'll be able to constrain the spectrum of cosmic rays and the role of cosmic rays in heating chemistry and coupling to magnetic fields. If this works on one cloud, we can use it to many clouds, and you can place. The good thing is you see the cloud, you know where it is. You can choose, and these clouds are abundant in the galaxy. You can choose some clouds closer to supernova remnants, for example, where you think cosmic rays are accelerated, some are farther away. Also look at the fluctuations to constrain the diffusion coefficient of these low energy cosmic rays. There's plenty of things you can do. And this is all thanks to JWST, which is launched hopefully next month. So with this, I'll summarize these two directions called cloud as cosmic rays detector, where we may be able to use infrared or radiation to constrain the population of low energy cosmic rays, their sources and their propagation modes. And supernova and 3D dust mapping, where we saw that supernova can act both as a way to destroy clouds and also to form clouds. And 3D dust is a new way in the study of the interstellar medium that will help us reveal the structures and supernova acting on molecular clouds in the ISM.
Act only toward not allowing you to form, right?
No, the cosmic rays.
It's only one.
Yeah, they just heat the gas. They do help in chemistry to, for example, the formation of molecular hydrogen, for example, in the early universe, not in our galaxy, but for example, in first galaxies in the universe where you didn't have any dust, cosmic rays produce electrons which help form molecular hydrogen that contribute to cooling. So in this way, cosmic rays can also help to cool clouds and form clouds. But generally speaking, in most cases, yes, they're negative. So the cosmic rays make ionizations. So it's the same way. If you have some galaxy that has already some. Yeah. No, you need to form them first. Yeah, but once you have them, they can help catalyze the chemistry, and thus also in a way they catalyze cooling. But this is not the normal set. In any case, so well, this I'll summarize, and if there's any questions, any further questions, I'll be happy to take them. Thank you.
Hello. Yeah, thank you very much for the nice talk. I have a question actually concerning the compression of the gas between the supernova. So how common is such an event? I mean, do you have enough supernovas that like go off at the same time that you really get like these like voids that basically expand at the same time and compress?
Right. So
how likely are the events?
That's an excellent question. That's basically touching on a larger question of to what extent supernova is positive or negative to star formation. And to give you a very full answer, I can't give you now because this is what we're looking at now at the map. I can show you something. This is a recent paper, this one that was just accepted to Nature, where what we show here, this is the peritone shell that we saw before that I showed you here. And this is the blue is the local bubble that is known for a while, for tens of years, where we're inside this void cavity of hot gas. And now this 3D dust, it gives us a very precise boundaries to this local bubble. And what we find is actually the local bubble is touching and has the same shape and touching the peritone shell. So we think this, what we're seeing here is the Taurus molecular cloud on the close side to us. So we are here. This is the shell, this is Taurus, this is Perseus, torus is actually in between the local bubble compressed, and on the other hand by the fertile shell. So for example, at least this one is an example where you have this interaction of two shells. That's what you asked,
Yes,
right?
yes.
So at least we have an example for this, but to really answer this statistically, this is one of the follow-up projects we want to do with this large-scale dust map.
Okay.
And if you have ideas for how to do it, in a machine way, like not just by eye, that we can talk.
I'm not in the field, but
Okay.
it was interesting to see.
Can you use your dark molecular clouds and other techniques?
Yeah, no, that's an excellent question. Right, Sarah. So we talked about it a little bit before. So I mentioned cosmic rays for when I spoke about the dark clouds, the cosmic ray, they penetrate inwards and they ionize the gas producing electrons. But actually, if you go near X-ray sources, the X-rays also penetrate in a similar way as the cosmic rays. And they also produce these secondary electrons, and all the same effects also hold for X-rays. So I should have said it from the start that this method can be used to detect cosmic ray sources or X-ray. There might be a degeneracy, but if you have a source that you know that it's producing X-ray, you think it's producing X-ray, this may be a way to tell you how much of X-rays are produced in the source nearby. Yeah, thank you for reminding me.
You already have the JWST time?
No. So we plan to with Sirio is Sirio Bialy here. He got a mid-sized project on JWST, and he was positive that we'll get time, and I hope so. But we'll propose for the next cycle. So far, we're just publishing the MMT observations that I showed you before. It's just actually the paper is on archive, I think today or something like this. Yeah.
Usually, what's the time scale till from lunch to data?
From lunch to data. I don't know. Daniel, do you know how much time before JWST start giving the data from lunch? Not lunch, but lunch.
I don't know. I imagine it'll be something like
Half a year or
like 6
so?
months.
Yeah, half a year. So maybe half a year from now. But first we have to propose, that's half a year, and then another maybe half a year, so maybe a year, maybe next colloquium.
Maybe I was. Can you repeat how you do the 3D picture? Sorry, you certainly said it, but this is kind of.
Yeah. First of all, it's not me. It's an array of computers of other people at the Max Planck Institute. But what they do is imagine you have two stars, one after. Yeah, Lev asked me about the 3D. Imagine you have two stars. I mean, in very simple words. In reality, it's much more complicated how they do it with all the theory information and all the machine learning and all this. But in simple words, you have two stars, and you see that this star should emit from the black body spectrum and everything you need. It should emit this spectrum, but you see there is some extinction. So there is something that is missing. And then the next star, you see there is this much missing, but a little bit more. So you know how much dust there is between these two stars by how much more the next star and next star and next star are extincted by this dust. So you know how much dust there is. Now from Gaia do the parallax, right? It's like eyes. You have the parallax measurement from the Earth orbiting the sun, and you see the stars from two angles. So from this parallax measurement, you know the distance to the star. So you know how much distance there is, and now you know how much material, so you know the density.
But it's all under the assumption that the media is the density of the media, what makes the extinction is relatively constant, right? That there is no.
You get the mean.
Density.
You get the mean. You get
the mean of that.
You get the mean density between these sources. You don't know the substructure. So that's what basically limits your resolution. So we can go down to roughly the resolution of the distance between the stars. You can't go below that, but you can go down to this resolution. So you know that in between the stars, there's this density. Between these two stars, the mean density is this. So you can go down to about 1 parsec resolution. This is the distance between stars in our neighborhood.
So you need to have stars inside the bubble.
You need to have stars. Yeah, and you have stars everywhere. But yes, you need to. You have stars every 1 parsec. This is 160 parsecs in diameter. You have stars every parsec.
So there is kind of assumption, and if its assumption is wrong, maybe the picture is
Well,
very
yeah,
wrong.
for sure, no doubt that this 3D dust map is approximate. There is some assumptions that go there, and if you ask me, okay, the dust map tells you that the density here is 20 particles per cc. Well, there is an error. It might be 15.
No. The question is, there are two alternative ways.
Our picture is not sensitive to this uncertainty because it's on larger scale. If we were to test a structure that is on small scale of this 1 parsec order of 1 parsec resolution, then it would be in a problem. But since the structure is on scales much larger than this 1 parsec, but maybe it's not exactly this shape, but a little bit other shape. Maybe the density here is not 20, but 50, but still the structure as a whole is quite robust.
Okay, let's think again.